Sorry about the sound issues that I was having before, so I think I've got them all worked out, so hopefully this will work today. So we're going to look at section 3.3, which is a geometrical approach to systems. This is some vocab that you probably ran across on the homework from last time. A feasible region, which is just basically this shaded in area that you're going to have from all your different lines. The boundaries are, of course, the lines that go around that particular shaded area. Last section also talked about the corners, which would just be the 2 points of intersection of those different lines that intersect there. A bounded feasible region is one where the sides are all straight lines and that it's contained within an area of some sort. An unbounded feasible region would look something like that, where there's one section of it or maybe several places where I can cut it off here and here, but I don't get to cut it off in any of this area. So it would be an unbounded feasible region. And there will be some cases where the answers are not going to be able to be found to the problems because it's an unbounded region. And then there are going to be a few cases where I am still going to be able to find an answer even though it's unbounded in this direction. I can actually find an answer if I'm looking for answers that would be in terms of what it's going to stop it in this particular place. And again, that's going to depend on the problem. Excuse me just a sec. Okay, so we can look at one in terms of, first of all, let's look at the steps that it's going to take to do that. So we have step number 1, define the variables. Step number 2, write a system from inequality. Step number 3, graph the system. Step number 4, find the coordinates of the vertices of the feasible region. Step number 5, write a linear function to be maximized or minimized. Step number 6, substitute those coordinates and vertices back into that particular function. And step number 7, then select the greatest or the least one. And again, the question is going to be to answer whatever the problem asks you to answer. So on this video, what you're going to see is, in the interest of time and effort here a little bit, I'm going to go ahead and I'm going to show you what they look like in terms of some ones that have already been done. And then you can go from there. Most of these examples are going to be from the textbook, but I just found this one online. So I've got a nice little system here, and I graphed these 3 equations. So here's the graph for y is greater than or equal to -2. Here's the graph for x minus 2y is greater than or equal to -1. And here's the graph for y is greater than or equal to -2x minus 4. And I found my feasible region. Okay, so now I'm down to what's my function to be maximized or minimized. So that would be f of x comma y, which would be 4x minus y. And this says find the maximum, and it also says find the minimum. So what I need to do then is I need to find the coordinates of these 3 points, which are the boundary corners of my feasible region. And then step number 6 says substitute these ordered pairs into this function to see what you get. And so if I use 3, -2, then I get 10. If I use -5, -2, I get -18. And if I use 1, -2, then I get 6. So the maximum occurs at this one, and the minimum occurs at this one. So again, basically there's 7 steps for me to follow. It takes a lot of time to work through all of these. That's why I said on this video, I'm just going to show you some that have already been done. And that way you can sort of look at those, slow down the video, stop it, work through it with it, and see what you can come up with for answers then. Okay. So your homework is going to be from section 3.3. And so I've just done some of the problems that are on that section. So looking at page 243 and 244, number 30, again, I graphed each one of those. And then I came up with a feasible region that looks like this. Let me see if I can zoom out a little bit and see that. I take each one of those corners, and there they are. I put them back into my function that I want to maximize or minimize. On number 30, it says maximize. And so I have two places where there's a maximum. So at either one of these 2 points, I would find a maximum. As a matter of fact, from 0, 10, which is here, from 0, 24, which is here, to 12, 20, anything actually on this line is going to give me a maximum. Okay, so looking at number 32. Number 32 asked me to graph these 4 inequalities. So I graphed them, and I ended up with a graph that looks like this. It stops here, it stops here, it stops here, and it stops here. But it is unbounded. Now, if I'm looking at number 32 and it says find the minimum for that, then I would be able to test these 3 points and test a point out here and see whether or not it got a minimum. But on number 32, it asks for a maximum. And so you can see from the bounded region here, there's not going to be any way to maximize that. So this would be an unbounded region where there is no maximum for that problem. Number 34, you can see the same thing happens there. There's that. Here's my region. And again, if I were to minimize that, I'd take this point, and this point, and see if I could find a minimum value for that. But number 34 asks you to find the maximum. And so again, this unbounded region has no maximum. Okay, so you can keep going with that and try a few of those. And then your homework assignment goes on with section 3.3. And there are some word problems. And so I'm just going to go through a couple of these with you to see what you can come up with. And then we can talk about what the answers are. But on 38 through 44, it just says to set it up and don't try and solve it. The setup of it, of course, is to take this information and come up with your constraints and your maximum and minimum function. And then from there, you do just exactly what was on the other problems. You graph them, you find your feasible region, you take your corners of your feasible region, you put them in there, and you determine whether it's a maximum or minimum. So number 42, just want to read it over with you. Metro manufacturer makes a single product on 2 separate production lines, A and B. The company's labor force is equivalent to 1,000 hours per week. So here I have 1,000, and this is in terms of hours. And then it costs $3,000 overlay weekly for operating cost. And so I have an operating cost. Okay, the next thing for me to consider is how many hours it's going to take for A and how many hours it's going to take for B. So it says it takes 1 hour and 4 hours to produce a single item on lines A and B. So 1 for A and 4 for B. And then the cost is $5 on A and $4 on B. So my one equation comes from 1x plus 4y. Notice I called that x and this y. 1x plus 4y is less than or equal to 1,000. And then my cost for that would be 5x plus 4y. It's got to be less than or equal to 3,000. And then it goes on to say how many items should be produced to find in each line to maximize total output. Total output. You have to make A, you have to make B, so your total output would be x plus y. And so that's the one that you want to maximize. Maximize this particular function. Okay, so, and that's all it asks you to do for 42. So let's try it again. Number 52. Number 52 says, beauty products make two styles of hair dryers, the Petite and the Deluxe. It requires 1 hour of labor to make the Petite. So there's that. 2 hours of labor to make the Deluxe. Okay, so there's labor. The materials cost $4 for the Petite and $3 for the Deluxe. And it says the profit is $5 for a Petite and $6 for Deluxe. So again, this is just my way of saying here's X, here's Y. Write the information down so that I can read it and see if I can understand how to put it. I know that X has got to be greater than or equal to 0. Y has got to be greater than or equal to 0 because I don't want to make negative items. And so now then I've got a labor and I've got a cost. It says the company has 3950 labor hours, so labor hours, I can't go over that. So 1x plus 2y is less than or equal to 3950. And it also says that in a week the materials budget is $95.75. So the materials here would be cost for the item, so that's 4x plus 3y. It's got to be less than $95.75. And then it says how many of each dryers should be made each week to maximize the profit. Well, the profit comes from 5x plus 6y. So P of x comma y is 5x plus 6y. So I went ahead and I graphed those. And it gave me this nice feasible region from here to there. And that's over there somewhere. So then I went ahead and found those feasible region corners, which is here and here and here. So there are 4 of them. 1, 2, 3, 4. And then on number 52, how many of each should be there to maximize? So if you put this number in there, that's 0, 0. If you put this in there, I don't seem to have that on there. And I don't have this value on there. So you can calculate the values. It turns out this is the maximum point right there. So that's how many they need to make each week in order to make the most money possible, given how much it takes time and money to make that particular item. Okay, so this is talking about basically a way of solving systems of inequalities, which is not systems of equations. These are graphs. So graph them, find your corners, put your corners back in your function, and then you'll be able to find out a maximum or a minimum profit.